In circuits, energy does not always change smoothly or instantly when a switch is turned on. When a resistor is combined with an inductor, the current begins to evolve gradually instead of changing immediately. In this lesson, we will learn RL circuits and how inductors create time-dependent current behavior in electrical systems. An RL circuit is an electrical network composed of a resistor and an inductor connected together in series or parallel. This simple combination produces one of the most important dynamic behaviors in circuit theory, where current does not change instantly but evolves over time due to energy storage in a magnetic field. The inductor introduces magnetic energy storage into the circuit, while the resistor controls how quickly energy is dissipated. This interaction defines the transient response of the system. Unlike purely resistive circuits, RL circuits require time-based analysis because the current depends on both present and past conditions. RL circuits are fundamental in understanding real electrical systems where inductive effects are present. They are widely used as basic models for motors, transformers, and many electromagnetic systems, where magnetic fields play a dominant role in energy transfer and storage. When a voltage is applied to an RL circuit, the inductor initially resists any sudden change in current. At the moment the circuit is energized, the current starts from zero and gradually increases as the magnetic field builds up around the inductor. This increase in current follows an exponential function governed by the time constant, defined as the inductance divided by resistance. The time constant determines how quickly the current approaches its steady-state value. After several time constants, the circuit reaches a stable condition where current becomes constant. When the voltage source is removed, the inductor releases stored magnetic energy, causing the current to decay gradually rather than stopping instantly. This controlled decay is essential for understanding energy flow in inductive systems. The RL time constant represents how quickly current can change in response to voltage variations. A larger inductance results in stronger opposition to current change, increasing the response time. A larger resistance, on the other hand, dissipates energy more quickly and reduces the time constant. From a physical perspective, the inductor acts like inertia in a mechanical system, while the resistor acts like friction. Together, they determine how quickly the system can respond to external changes in voltage or load conditions. This behavior is fundamental in dynamic circuit analysis because it defines how energy is stored and released over time. RL circuits are often used as simplified models for more complex electromagnetic systems in both theory and practice. In practical engineering, RL circuits are widely used to model systems where inductance plays a significant role. They are essential in power electronics, motor control systems, and electromagnetic devices where current cannot change instantaneously. Engineers use RL circuits to analyze switching behavior in inductive loads, such as relays and solenoids. When switching such devices, the transient response must be carefully managed to avoid voltage spikes and energy losses. RL analysis is also important in signal conditioning and filtering applications, especially in systems where inductive components influence the frequency response of the circuit. In RF engineering, RL effects become increasingly important as frequency increases. Inductors contribute frequency-dependent impedance that shapes signal behavior in transmission paths and matching networks. RL behavior is also critical in understanding losses, phase shifts, and signal attenuation in high-frequency systems. Many RF components exhibit inductive characteristics that must be accounted for in accurate system modeling. Understanding RL circuits is essential for transitioning from basic circuit theory to more advanced RF and microwave engineering concepts, where dynamic magnetic effects strongly influence system performance. In this lesson, we learned that RL circuits combine resistors and inductors to create time-dependent current behavior governed by exponential response. This behavior is defined by the RL time constant and is fundamental in modeling inductive systems and transient circuit response. In the next lesson, we will explore RLC circuits and understand how resistance, inductance, and capacitance together create resonance behavior. If you found this useful, like the video, subscribe, and follow for the next lesson.